group of somewhere between a few hundred and a couple of thousand people who are anxiously awaiting you pressing that go live button.
Yeah, we are live, so we should be coming up on all platforms momentarily. Max, as we've mentioned to you, and as we mention every single time the first couple of minutes, we just want to make a few community announcements and let the people sort of trickle in while we double check that the audio, so the sound and the video is coming in correctly. Dave, do you want to kick us off with a few comments?
Absolutely. So I'd like to kind of take this as an opportunity to do a bit of a reset on the community comments. So in the past, we've talked about upcoming events that we know that are going on with us. We haven't necessarily done a good job of talking about other events, and because people historically have not sent them. So I have a couple of events to talk about, and I want to invite everyone to go ahead. And if you have an event that you want listed for us to chat about briefly in the beginning, to please go ahead and drop that below. Don't drop that below. I won't look at it, but send me a message or send us an email, and we will make sure to go ahead and get you on the list. So if you guys remember all the way back to episode 46, like 5 weeks ago, Alan Ray was on, and he was talking about collaboration and how the industry needs to collaborate. I don't know if Alan is part of this, but coming up on March 16th, there's a live virtual workshop called Integrate Live. So Alan may or may not be part of it. I know he's posted about it. The goal is to have an open community collaboration. Vertec is going to be there. Canary is going to be there. We've talked about Canary in one of the earlier episodes. They do process historians. Kepler is going to be there, and there will be a few other places being there, talking about leveraging IIoT, PLCs with MQTT, and sending that operational data to the cloud. And their whole goal is to be open and transparency, and they're going to talk about pricing and all of that, which I think is very interesting. So I'm going to go ahead and drop a link down below in the chat. Again, the inaugural Integrate Live virtual workshop is March 16th at 11 o'clock in the morning. So I've gone ahead and dropped a link in the chat for that. And I actually also have another one. Up until about 3 minutes ago, Vlad, I wasn't sure if I was going to be able to say this. And as we kind of always do, I was thinking to myself, do I say it or do I wait? But luckily, I did get the yes. So ISA is having an IIoT and Smart Manufacturing Conference. It's officially been announced for March 30th, which is a Wednesday. So you guys can go talk about IIoT and then come hang out with us. There's going to be a jam-packed list on the schedule, and I know because I'm part of the conference committee, and so you guys should absolutely go ahead and check that out. So their link is iiot.isa.org. I will also go ahead and drop that in the chat if you guys are interested in taking a look at that. But both of those should be fun. And again, I will make the comment of if you guys are looking to go talk about your events. The first 5 minutes of this is very much a community related show. Please go ahead and send me a message or send us a message through the website. Now, beyond that, Max, I always embarrass Vlad. And the number one thing I embarrass Vlad with at the beginning of the show is you may or may not know, Vlad has a very popular YouTube channel called Solus PLC. Hey, everyone on Solus, we are also streaming to those guys. He has 28,000 subscribers. He talks about, well, kind of all of this industrial stuff. And then we also have the show on here. Vlad won't ask people to subscribe to his own YouTube channel with 28,000 subscribers, Max, but I will go ahead and ask. So if you guys are not subscribed to Solus PLC, you're absolutely missing out. So please go ahead and do that. And I think that has officially checked the box in Dave and versus Vlad in
Thanks,
Manufacturing Hub Bingo. You're absolutely welcome. Beyond that, we want to, again, shout out Siemens for sponsoring this robotics theme. We're super excited about that. And without further ado, let's go ahead and jump into it. So everyone, welcome to Manufacturing Hub. I am Dave. This guy up here is Vlad, and we are kicking off a robotics theme. Luckily, we have Max Kirkpatrick here with us, who's going to tell us a lot about robots, because once again, Vlad and I don't know very much about robots. But Max, so without further ado, welcome to the show. Thank you for being here.
Yeah, absolutely. Nice to be here.
Really appreciate your time. Go ahead, Dave. Go ahead.
Absolutely. So I was going to say, if you guys haven't heard our talk about digital twin and virtual commissioning, Colm was on episode 40. That will be a very good precursor to a lot of stuff that Max is going to talk about software-wise on robotics. But can we kind of just jump in, Max? Can you give us a little bit of your background? How do you get to have, I don't know, $500 million or whatever it is of robotics behind you? You got 4 or 5 robots. You got a 3D printing machine. How did you get here?
You might be off by a couple orders of magnitude, but yeah. So I'm a robotics engineer for Siemens. I have been in this position for the last maybe 3-4 years now, just about 4 years. I graduated from the University of South Carolina in 2018 with a degree in mechanical engineering and a minor in computer science. And even before that, I was doing all sorts of fun work with robots. So I think I started in labs on campus programming my first industrial arms. And before that, it might be some people that are familiar with FIRST Robotics. I was on FRC team in high school, right? So I started doing this kind of stuff a while ago. But I guess I got a passion for it, and I kept trying to learn how to program and learn how kinematic devices work and all this stuff, and got to the point where I got a job offer from Siemens to take on this consulting position, this robotics consulting position, and took that, and then got a whole lot more experience in the field with robots and robot programming and simulation. And I guess that's basically the gist of it.
Max, if we can dig into the education, path a little bit more, I'm curious, to hear your perspective now that you're doing a lot more, I would say, industrial robotics. What was the thought, and I guess like in retrospect, going into mechanical and getting a minor in computer science? Would you do that again? Seeing what you see now, what is your perspective on that?
I think, at least through the context of industrial robotics, I think that's like a very good path to go down. I think actually in industrial robotics, there's a lot more mechanical and like physics engineering kind of stuff going on than there is computer science. It's very useful to have the computer science background, and I would recommend it if you don't know how to program something, just learn how to program anything. But past the base level of understanding logical statements and being able to author something in like Python or something like that, you don't need a huge level of in-depth comp sci knowledge to know how to program most robots. But what you do need is this knowledge of mechanical systems. It's very useful to understand how robots will move. And like if you can understand things like loads and moment arms and kinematics and dynamics, it makes understanding what is going wrong in your robot cell a lot easier. Because in a lot of ways, the robot vendors take care of all of the math for you behind the scenes. But you need to be able to interpret what's going on. Oh yeah, very luckily, the inverse kinematics are complicated, but yeah, I think that background really helps.
And Max, if I may expand on that, how was the learning curve, right? So if I understand correctly, you had some exposure to these robotic arms while you were studying in your program. But if you were, again, maybe to start from scratch and learn robotics, what do you think are maybe the challenges of that, or how would you proceed like differently? What would be kind of some thoughts around getting into robotics and learning it from scratch to where you are today?
That's an interesting one. I think the biggest single piece of advice I have for people is to learn any programming language, and then that becomes a very good jumping off point for just about any kind of mechatronic system, no matter what you're programming. But for robotics in particular, like the learning curve was, I would say it's definitely got some steepness to it, right? Like you learn the theory in school, and you learn like, okay, kinematic linkages, and this is how we can invert a matrix and do some inverse kinematics. Maybe we need a pseudo inverse, all this stuff. But you don't actually have to care so much about all that stuff when you start working with the arm. You have to care about like, oh, as this arm moves through a singularity, it's going to rapidly rotate the joint, it's like J4, J5 around, and it could smack into something. And you didn't necessarily think about that when you were programming the path. Or you might have to care about deflection of the arm as you put a load in the gripper, or on the end of the arm, end of arm tooling, and you might not anticipate the 5 millimeters of deflection that you'll get when you try to lift up this 100-pound object or something, right? And these sorts of like practical considerations, and of course you can model the theory for all this and you can work that all out analytically, but no one usually does. So when you go to try it in the real world, things break and then you have to fix them. I don't think I've ever met a single robot programmer who can honestly say they haven't crashed a robot, right? I'm pretty sure every single one I've ever met has crashed a robot at some point.
Absolutely. I think it's just a rite of passage, so to speak. And I
Yeah.
think it happens fairly early on in your career, right?
Yeah.
And you realize
Yeah.
like what kind of a trouble you can run into. And hopefully it's just, minor damage or, end of arm tool that gets bent and can be put back into shape. But no, it could be, I guess robotics in general could lead to fairly disastrous consequences, right? And safety is a big part of robotics in general.
Absolutely. Yeah. Yeah.
But Max, I want to ask you, what are you maybe doing today with Siemens, and can you give us maybe some examples or use cases of what you're working on today?
Yeah. So my role within Siemens is as a consultant for our customers, and what I do is I'll build out simulations and programming environments for robot cells, lines, manufacturing floor setups in companies across the Americas. And this could be things like, the canonical example is robotic spot welding or arc welding in an automotive cell, all the way through to I've done drilling for composite parts. I've done automated fiber placements. I've done inspection of composite parts. That's all A&D stuff, but I've also done electronics box build kind of things, so like assembling electronic components. I'm very much work across industry, and what I tend to do is we will take our robots and, well, any vendor's robots, like the robots you see behind me, and then place them into a simulation environment where we can actually program and develop the paths completely offline, right? And that's what we would call offline programming. And we use a simulation suite for that to allow us to build and evaluate and, I guess, ensure that everything's going to perform the way we expect it to when we hit run, right?
And Max, that's one of the misconceptions that I think Dave and I had when we spoke to Clint. And again, this conversation happened a little bit off stream, but Siemens is not necessarily the manufacturer of a lot of these robotics arms, but they do come in on the simulation side. And a lot of times, again, coming from a food and beverage background, it was perhaps not the connection that I've made initially. It becomes really important to simulate these applications in automotive environments where the complexity is highly increased. Could you talk a little bit more to us about, Siemens's involvement in robotics specifically, and where do these tools come into play?
Yeah, so that's absolutely right. Right, we don't make our own robot arms. There's no teal robots. We deal with the orange ones and the red ones and the white ones and the blue ones. Bonus points if you can name all those companies. But those what we do is instead we build simulation models of the systems that we're using, and in cases where the complexity is very high, let's say we have 20 robots all working collaboratively in a automotive line, right, where everything needs to be synchronized, and if one robot moves out of turn, you could be crashing multiple robots and many hundreds of thousands of dollars in end of arm tooling. It pays a lot of money to get it right the first time. And so that's where offline programming tools come into play. And there are other, a lot of the vendors out there for robots have their own offline programming tools. But what we do inside our tool, which is called Process Simulate, is we can take in all the different vendors. We can program just about any robot you can buy off the shelf anywhere, and we can have as many of them as you want in a cell. We can load all sorts of other geometry and other devices. We can implement PLC programs inside the simulation environment. There's a lot of capability that we have that lets us, evaluate just about every facet the robotic cell before we deploy any code to the system.
Gotcha. And Max, if you can mention a couple of, I guess, the software tools and how they tie in between each other. We have that question in the comments from Malachi Greb, who's a systems integrator. So he's curious about, so traditionally, you'd come in and program, let's say, a Fanuc robot in their own like native language, but how does it get translated into the Siemens world, and how does it tie in? Also, on my side, I'm curious a little bit on the PLC side. How does that tie into TIA Portal, for example?
Yeah. So the first question on just the robotics side, if we would just say we had one of these robots behind me, these are Yaskawa robots, and we wanted to program one of these, what we would do is we would create the path in 3 dimensions, or I guess 3 dimensions plus the 3 rotational components. We would create that path in the software, taking into account all the collisions and weight conditions and anything else that we want to have in there. And then we would post that to the robot's native syntax using a post processor that runs on our software package, right? So inside Process Simulate, we would right click on the operation and just say download to robot, and it would post using the configured post for that machine. We have posts for, like I said, just about any major vendor you can think of, Kuka, Kumau, ABB, Fanuc, Yaskawa, all the big names. On the PLC side, what we do is we integrate with PLC Sim Advanced. And what we can do is we can actually evaluate the signal states of the simulated cell and send those states back to PLC Sim Advanced over an API. And so you might have your portal project running on a virtualized PLC. And then that PLC will say, let's say I have a conveyor and I'm just going to turn off the conveyor when a part gets to a certain location on the conveyor. So I have a sensor, I have a conveyor, and it's just a light sensor, right? So when the beam gets interrupted, conveyor stops. Easy PLC program. But without actually physically testing it, what we can do is we can have a virtualized sensor, we can have a virtualized conveyor, we can have the virtualized component on the conveyor. And as that conveyor moves forward, the box will eventually interrupt the beam. And then the simulation will send the signal to the virtualized PLC to say, hey, your beam has been interrupted. And then the PLC will say, okay, beam's interrupted, I'm going to stop the conveyor. And it sends that signal back to the simulation. So it's a two-way communication with PLC Sim Advanced that allows us to pull in PLC code and actually have a virtualized PLC control just about every facet of the cell.
Yeah, and that's I think we've had that again discussion off stream with Colm, but it's really interesting that you can simulate again not just the robotic arm, which is I guess what I thought was a robotic simulation software, but also other components that would be a part of that cell, right? So you can most likely simulate the gates, the sensors, any like end of arm tools that you could mount on that arm, and probably product as well that's coming in on a conveyor belt with certain variations of that product. So it's it's definitely really interesting. Dave, before we dive into higher technical topics that I'm very interested in personally, I want to give you a chance maybe to ask a couple of questions as well.
Absolutely. No, I appreciate it, Vlad. So, Max, we were talking with Colm again a number of weeks ago, and he was describing through digital twin and virtual commissioning how he was able to help some of his clients reduce the time from purchase order through visualization to completed machine. Like typically that process would be about 2 years, and I think they got it down to 6 months for some of the machines. And I feel like that was a very eye-opening conversation point. Do you have like an example, either greenfield or brownfield? And again, it doesn't have to be a specific customer, but could you just like walk us through what the typical process looks like for you to go simulate robotic arms as part of I assume like a digital twin?
Yeah, absolutely. For a greenfield example, the lab that you see behind me is actually a lab on the campus of the University of South Carolina, where I am. I got my undergrad there. I'm currently getting my master's there as well. And this is a lab that didn't exist at all 2 years ago. Right. And I think we got it. So the state that you see behind me is maybe this is like 6 months old now or so. But we got from napkin sketch to robots on tables and everything, running the full system. It took us less than a year, I think. took us maybe, I think it was about 9 months total. And what that process looked like was, we started with just the blockiest, like most rudimentary simulation you can possibly think of, where you could have drawn it up on napkins or flip cards and it would have been the same effect. And we started by just modeling up where we wanted parts to go at what times. And then we started breaking it down into, okay, well, these are the individual operations need to do that. And then we said, okay, well, where can we place stuff physically so they can reach all the things it needs to reach? And then we wound up with a few layout alternatives. Once we have those alternatives, we then do a little bit more analysis on each of them, and then we filter down onto what we want. And we use the same simulation tool all the way through this. So we're sort of maturing our model as we go from just boxes, like literal boxes of like, this is the reach volume of this robot. We just chuck it on the table and we say, okay, if the robot's in the middle of this sphere, this is what it can reach, all the way through to, okay, now we're actually simulating every individual operation that the robot's doing. And then finally, we go to, okay, we've actually programmed these, we've generated offline programs, and we have generated PLC code, which was a different story, but that we have our PLC program, and then we can connect those two together and actually watch the whole cell with the virtual HMI, virtual PLC, all controlling the virtual cell. And I think from inception of design and the granting of the money to get this done, so to the point where we actually had robots up and running and able to execute a task, was probably about 9 months, which I think for a 5 robot cell is pretty quick in my experience.
Yeah. So if I'm a manufacturer and I have, I don't know, we'll call it unlimited budget, right? Is 9 months from saying, hey, Max, I know I want to put, a number of robots in this place to do this series of tasks. Is that a realistic time frame? Is that a very aggressive time frame?
So if you're using, the simulation tools and you're using, I guess, all of the software to its fullest extent, I think that's a fairly reasonable time frame.
Okay.
It doesn't seem overly aggressive, but it also doesn't seem overly conservative,
And Max, do you think we're going to, I guess, looking at the robotics industry, and I think you would probably agree, but also want your opinion on this, there's going to be a growing demand obviously in automation, but robotics specifically, again, due to, we would say, COVID, but ultimately, I would say not enough people to be able to fill certain jobs that are fairly straightforward, I would say, to automate to some degree. What are your thoughts on, I guess, the changes in the industry with that regard? Is it going to drive faster robotics? Is it going to be faster to deploy? Simulation, I'm assuming, is going to grow because, again, the turnaround times need to be shortened. What are your thoughts in general?
Yeah, well, so one thing that's happening right now is there's massive lead times on just about anything you could possibly want to buy. And so one thing we can do is make use of that time, that dead time, through use of simulation, right? If I know exactly what everything's going to do and it's just sitting on order, well, why don't I just program it now and do it beforehand? So that's one area where we've seen a lot of interest, is we can just program up front, and then when they get in the door, it's like, okay, no, now we can just turn the cell on. That's one area. I think another thing is there's a lot of demand for people that know how to do this level of work, that know how to do this, and I think that demand is only going to continue to increase. Robotics and automation as a field isn't going anywhere. In fact, I think it's expanding into more and more spaces. It used to be we would always say we want to automate the dull, dirty, and dangerous tasks, right? But now we're also talking about, well, there's some dull tasks that people do that we've just said weren't possible to automate before, but now, maybe we can actually automate that. Maybe through use of cobots or AGVs, we can actually start to automate some of these tasks that were previously thought weren't possible. And I think that's definitely coming down the pipeline, if you will.
Yeah, and we'll dive into that a little bit more, because I know you're doing a lot of you're writing your master thesis, and obviously we'll discuss that a little bit. But again, I think it's really interesting to see all the changes in the robotics space. I wanted to ask you, what about controls from a PLC versus controls on the robotic, because I think, again, me and Dave had this conversation a while ago, and again, I think it opens a lot of opportunities from the sense that if you have software, again, that's standardized across different vendors, it offers a unique opportunity to make it much easier. Even, from the standpoint that you mentioned, there's a lot of engineers trying to learn these different platforms, and there's not enough people to just fill that gap. So why not make that learning curve a lot less steep?
Yeah, and I think so. PLC based robotics are very interesting. There's actually some efforts from Siemens and from some other companies as well to try to build standardized libraries for PLC programming of robots. And this would be like, I have a SIMATIC PLC, like a S7-1500 or something, and I just basically plug it into a KUKA robot, and I say, okay, KUKA robot, you're just going to listen to everything I say now. And so instead of the KUKA having its own, programs on board, it's going to have a bunch of commands that we can call up from the PLC, and the PLC just specifies the path in real time and sends those coordinates to the robot, and the robot just moves. It's sort of like a dumb servo, right? Or rather, a really smart dumb servo. But
Yeah.
that has so the advantage, of course, is that you could do any number of robots from any different number of brands the same way, right? So I could have 5 different robots from 5 different manufacturers, and I could have one PLC guy that knows how to write ladder, who could program all these robot systems for me. The disadvantage is that because you're trying to span across platforms, and because you're trying to do this on a PLC, it typically in ladder instead of in a text-based programming environment, you're typically limited on what you actually can do with a system like this. So KUKA and FANUC and ABB, they have a lot of differentiating selling points that they like to use as saying, this is why our ARM is the best. They're probably not going to be overly thrilled about releasing that on an open platform. And so what that means is that some of these advanced features might not be available to you. This might be something that's really good for like a machine builder who has like 2 or 3 arms in conjunction with a bunch of other moving pieces, and they just need to move to a couple positions, but realistically they aren't doing any sort of complex curve following or spline work, or maybe not doing any visual inspection. These sort of like force feedback advanced topics in robotics that are just starting to come into the field, they probably aren't going to be supported on PLC directly for a while now. And that's where, tools like ProcessSim or any other offline programming suite would let you do some of this stuff that is specific to each robot, but still have a common background to program in, right? So that's where I work, but I definitely see the usefulness of a solution like that. I just don't know if it's at the point today where I would say every robot I purchase, I want to program with a PLC. I think that there's still a lot of capability that's not there yet.
And to Max's point, I met one gentleman back in 2017 or 2018 who was building robots without controls on them. But basically every large manufacturer, whether they be, yellow or orange or blue or white, they're going to sell you a very expensive controller on there. And well, I know some people crazy enough to have been ripping off controllers for more than a decade. That's because there were very specific use cases that the tolerances on those controllers weren't enough. So trying to control via PLC is certainly not a less expensive option. And then if we try to have the PLC programmer, so we generally already don't have enough of, try to now program robots, I think that could certainly cause a number of issues, because many of them may not be used to kind of all the quite physical motion of those robots and what that can do.
That's like what we started with at the top of the call, where I mentioned that having a mechanical background is actually quite helpful in robotics because these things move, right? And a PLC programmer might not be overly familiar with like the way in which robots move. That it might have always been the robot guy's job. What I will say though, as an advantage of these types of systems where we have a master PLC that's directly controlling a robot like that, is that debugging on the shop floor becomes a lot easier. I mean, there's a lot more people out there that know ladder than that know every single robot programming language, right? And it's one less place to look for problems. So you don't have to pull up the teach pendant and start. You can just be on your regular HMI and look at that, or you could just open a portal and go online and look at your ladder rungs and see what signal is missing, that kind of thing, as opposed to having to use two separate environments and try to trace signals back and forth between them. It really can be a mess, right? And that's that system integrations hell that everyone hates, right? And I'm sure there are some system integrators listening that are very familiar with that integration hell, right? So that certainly can be a benefit.
No, absolutely. And I think all of us have been in there, in that situation. Dave, did you have a comment?
I would say, kind of to Max's point, is I think many of these are complicated, and when you have 2 or 3 or 5 systems, there are so few people that are experts at any one of those systems, it just becomes very difficult. I chatted with a group kind of at the beginning of the pandemic who kind of found this strange niche in building a software platform that allowed people to do a better job just specifically on their welding robots, because they find a lot of people buy welding robots and then they can't actually get the welding robots to do welds that will pass inspections. And so they found it was a super simple overlay of a screen, but they found that if they go and kind of set the robotic arm up correctly, they can let you punch in, your 4 or 8 actual pertinent points of information, and then the robot can weld. And so I think simplification, whether it's through PLCs, whether it's through standardized libraries, whether it's through more people have a better understanding about how to use these specific robotic languages, I think we need to find a way to simplify more in order to do a better job pushing robots out into manufacturing facilities and then implementing them successfully.
Yeah, and I think that my only add on to that is that we need to, I think, focus on what I would call targeted simplification. Because if you have a robot, you just try to dumb down everything. Congrats, you just stripped away all the functionality of the robot. You can now go from point A to point B, right? I mean, we can do a whole lot more than that now. What you need to do is have like application specific simplification. So, and this is the job of engineers in general, right? I mean, this is like my job. This is a job of robotics engineers the world over, to try to find ways to make systems usable to people that aren't robotics engineers. But if you start pulling away all of the complexity, then you also lose all of the functionality. So you have to find that balance somewhere in there, especially for the use case that it works very nicely. And for PLC based systems, I think that right now we have a very good balance for simple use cases. So a very good balance for pick and place use cases, a very good balance for integrated inside, for uses where a robot is integrated inside a machine and is basically used as a positioner. Whereas, we might not have a very good balance yet for cobots or for, let's say, friction stir welding robots, right? I mean, there's certain levels of complexity that are beyond the scope of what we can do with PLCs right now. And some of those are beyond the scope, like you mentioned before, of what we can do with the controller that comes with the robot. I mean, there are some companies that say that your level of precision you can get out of that motion controller, it's not good enough for me. I need to, if I'm doing milling on the end of a robot arm, I need a better controller than what you gave me, right? So it goes both ways.
But I would say that there are probably very few companies that actually need a significantly better controller with better tolerances than what has come out. And we've kind of made leaps and bounds in the last 5 to 10 years of robotics. And so controllers are now certainly better than they are. And I would say every company that I know that is ripping off controllers is doing this in the process of, tens or hundreds of millions of dollars worth of cells that they're putting, because the value of what they're building is just that much. Absolutely. So I want to slightly shift the conversation to something that you brought up. You kind of introduced the concept to us a couple of days ago, Max, and I kind of want to let you introduce the concept to everyone else. So you told us about this crazy futuristic thing called soft robots. Can you tell everyone what this is, please?
Yeah, and if there's any soft robots experts in the audience, they might get mad at me because I don't want to put my foot in my mouth. But basically, the premise is that in today's robots, the robots you see behind me in most industrial settings, we have these 6-axis arms, or maybe sometimes 7 axes. or some external axes, but they're all like very rigidly defined single points of motion, right? So if I look at like these arms behind me, they have 6 axes. The first just spins it around the base, the next does the tilt, and then the next does the next tilt. All of that's very like rigidly defined. In a soft robot, the joints are no longer single points of motion, right? And this is going to start to get kind of hard to explain, but they're sometimes referred to as continuum manipulators, where instead of bending at a singular point between 2 rigid bodies, so they have like these 2 points and they just rotate at this location, right? They move around a fixed point. Now we have a unit that bends along its length, so the entire member, the entire link bends across its entire length. And that allows you to like curve around stuff. So you can actually like have an arm that can like curve around an obstacle because it can physically bend the arm around the obstacle. I mean, you could also think of it as having a robot with many hundreds of joints, right? Or many thousands of joints. But in reality, what it is a robot that's bending continuously along its length. And you can stack these on top of each other. You get sort of snake-like structures out of these.
And what would be, I guess, I think we discussed this a little bit again off stream, but the use cases, could you mention where this could be like interesting or solving like a very specific use case perhaps?
Yeah, so these sorts of things have a number of prospective use cases, but soft-sided robots are, I guess, first off, they're called soft-sided because usually they are like safe to touch. They have no pinch points, right? Because you can't imagine you have like a pool noodle. You can't like bend that pool noodle so sharp that it would chop someone's finger off, right? It's not ever going to happen. So they're safe to be around people in non-gated work areas, right? I can have this in an open space. And I can have this in someone's home, or I can have this on an AGV that's moving around a hotel or something like that. The other thing is that because they bend in interesting and different ways, they can reach around obstacles that a traditional arm wouldn't necessarily be able to. They can reach kinematic solutions that just aren't even things that you could conceptualize for a 6-axis arm. And this makes them more flexible for like assisted living environments, or environments where like home environments where the robot might need to be performing actions on behalf of a person who can't do them themselves, right? So this is actually something that I published a paper on a while ago in the RESNA conference, but this is I did some work in this, basically building a mock-up version of this, a 2-stage continuum manipulator that could reach around obstacles and perform these types of assisted living applications, like opening a door or getting something from a top shelf. And the fact that it was a soft-sided arm meant that it could function in an elderly person's home without having substantial risk to that inhabitant, right? So that's one application. There are a lot of other fields that these are also useful in. They can do things that are more closely related to how humans can move, right? And there's a lot of research in this field right now about trying to get robots to emulate human behavior. So that's also, like anytime you start thinking about, well, I couldn't really bend a 6-axis arm in that way. Well, you probably could figure out a way to make a snake-like or a continuum manipulator bend in that sort of way.
And Max, if we can ask you about the challenges of soft robotics, I know that we've already mentioned kind of at the beginning of the conversation the heavy mathematics involved in traditional robots. What does it look like in soft robotics, and what are some of the other challenges that you know?
So, I mean, the mathematics involved in a 6-axis or a 7-axis arm, I mean, it's inverting the matrix, and sometimes you don't have a singular solution, and so you have like these 6 different solutions you can choose from. We call those configurations, but at least there's like a solution most of the time. And at least it's, not an infinite number of solutions most of the time. Singularities exist, and we're probably all aware of those problems. But these issues are a lot more common when you start thinking about a robot that could be modeled as having 10,000 joints. because you might have 10,000 heavily constrained joints that correspond to the individual little bends in the arm, if that makes sense. And so we model these things as stages instead of individual discrete joints. And then we have to do all the physics and dynamics along the length of that stage. So imagine, think back to your solids class that you took in college, and you think about like, okay, well, the beam bending problems. So I'm gonna have this thing bend along its length. Well, how much force do I need to apply at what distance to make this thing bend, and what radius is that going to result in? And then do all that, but backwards, so that you can figure out for a given target position how you can bend the different stages to get to that target position. So you're like stacking up multiple beam bending problems on each other and then solving it in reverse, which is yeah.
So it's good to have a software background when working with, especially these robots, because I'm assuming the computing power required to do these calculations is quite extensive, at least at this point, right?
Yeah, I mean, obviously, when inverse kinematics systems for 6-axis arms first came around too, people were like, "Oh, this is really hard," and now we just consider it a trivial solved problem, right? I'm sure that this is going to get to that point eventually. Just like path planning algorithms are one of those things that is another area of research where we're getting substantially faster. It used to be that like path planning was like, okay, we'll just do A star. We'll just brute force our way through and find a solution. Now we have much better approaches to path finding, genetic algorithms. We have machine learning techniques that are much better at path solving than just brute force A star, right? And so we're like, I'm sure we will develop similar solutions for continuum manipulators and for other, like AGV solutions. We're going to find better computational techniques. We always have, but right now, yeah, it's the brute force approach is tedious, is what I will say.
No, absolutely. And if we can shift a little bit, Dave, before I let you jump in, one last question that I got from Max, at least for now. You've mentioned
Max.
you've mentioned cobots. I'm curious, your thoughts on like the cobot, not necessarily maybe market, but the applications that you see in the current space. Do you see that expanding? Do you see, again, in the industrial space, a lot more collaborative applications? Do you think that that's going to like maybe still be overshadowed by traditional robots? And at the same time, any other areas that you see expanding similar to cobots on any other like tangents from robotics?
I think anything that's done at volume will probably still be done by traditional robotics for the foreseeable future.
Mhm.
We might even see things like the safety barriers going away and being replaced by computer vision approaches to monitor human presence and stuff like that. But
Really? Okay.
yeah, that's a research area too. But I think the arms are going to stay the same in those high volume production areas. Like I said, there might be cost cutting measures to try to reduce the cost of setup and reduce safety overhead and these sorts of things with better technology. But I think the arms are going to stay the same. But the area I see cobots most used in is in low volume open areas. So like if I have let's say an application, well, and in applications where human positioning is much more accurate than robot positioning is right now. So one of the areas I've seen it was in lift assist, right? If I have a heavy object and I need a person to position very precisely at a location, a lift assist system driven by a robot is very much a viable solution for that. And I've seen multiple places where they've done that kind of thing. Other cases are any time where a manufacturer really doesn't want to have to put a cage around something, they can do the same application they were doing with a traditional robot with a cobot and just say, okay, well, now we're just going to speed limit the thing and we're going to have torque sensing on all the joints, and we'll make sure that if something runs into this, we stop. Right? Those are the two big areas where I'm seeing it. There's also some stuff being done with like robots working in and alongside human workspaces for like AGVs moving along in and alongside human walkways, and we might have AGV mounted robots. So we have like a robot that's mounted on top of an AGV that can deliver things to certain locations or perform maintenance at certain locations. But these are, I think, less I see a lot of companies looking into that as like being like, is this a viable solution? Is this something that we actually want to use? But I don't see it being used in production very much right now. Those, especially places where humans and robots are like very definitively sharing the workspace, it hasn't taken off quite as much as I think a lot of people expected it to. I think it's still coming, right? I think it's just harder than people imagine. One of the reasons that it's difficult is that the paths aren't known until they run. So you can't really make any guarantees about what this robot is about to do until it moves because, well, I mean, in a cobot situation, a robot may dynamically adjust its path to avoid a collision, or it may be actively being guided by a human, right? And then in those cases, traditional offline programming or teach-dependent programming doesn't make any sense because the path isn't static anymore.
No, that's super interesting. I mean, I have a lot more questions, but Dave.
There it is. I promise everyone that Vlad will say something to the effect of, and I have a lot more questions. We will talk more about the future of robots, and I specifically want to dig into that robot versus cobot and the applications that we use that in. Before we thank some people, Max, I do have one question. Now, this is probably maybe the strangest question that we'll ask today. So, soft robots or soft-sided robots. We talked about it kind of being the snake arm. As you were describing it, I'm kind of almost thinking like an octopus tentacle, right? Well, like because it can move around and it can grab things. So are they all going to be one, or are we maybe going to stack, a bunch of them together to be able to pick and maneuver a variety of different shaped objects?
There's definitely nothing that would guarantee that you would only have to use one, right?
Okay.
I think the only reason why you might say you should use one is because the level of complexity goes way up, right? You start saying you want to have coordinated motion of two continuum manipulators or two soft-sided robots. I mean, shoot, coordinated motion of two 6-axis arms is already very, very difficult, right? Those are some of the most complex cells in the world, where you have like one robot that's doing arc welding, another robot that's moving the part that the first robot is arc welding, right? Coordinated motion is hard. And coordinated motion of things where we don't actually have a very good model for how they move yet is even harder. So I think
interesting.
I think that's it's coming down the line, but it's far.
Yeah. Okay, so I understand what you're saying, Max. And so Vlad, my takeaway is manufacturing hub at some point will have an octopus-shaped soft-sided robot that we're going to take places, and it's just going to pick up things, beer cups and wine bottles, and then open them up and like pour the drinks, coffee. All of these things are very realistically doable generally within our lifetimes. So thank you for that, Max. I like that. But before we continue to get into the future, we have some people to thank. So Vlad, can you play the sound for us, and we can thank Siemens.
There we go.
Awesome. So as I mentioned, we absolutely want to thank Siemens for sponsoring this show and the entire robotics theme. Now, the technological tasks in modern machines and plants are diverse and often, are odd. Wow, I've completely lost it. Let me try again. The technological tasks in modern machines and plants are diverse and often demanding. It's good to know that there's a smart answer to all the challenges regarding motion control, signal acquisition output, closed loop and PID control, edge computing, artificial intelligence, machine learning with SIMATIC Technology and the SIMATIC Technology-CPUs. Now, Siemens is a global leader and innovator when it comes to motion controls, robotic, and simulation applications. They have one of the world's biggest investors in technology R&D. Now get this, Vlad. They're spending more than 6.11 billion, big B, US dollars per year, and they've maintained the investment even throughout the entire pandemic. Now, I want Vlad and everyone else to think what they could possibly be doing with 6.11 billion USD per year, and we should all be getting excited. So the integrated and scalable SIMATIC technology automation solutions save you valuable engineering time for simple tasks as well as for complex issues and guarantee maximum efficiency and flexibility. This means one engineering framework with TIA Portal, one control with SIMATIC Technology-CPU, one communication for standard automation, safety, and motion control with Profinet. I I think it's amazing. As I will joke, or as I will tell everyone, as we were joking with Max, episode 40 when we talked to Combe about digital twin and virtual commissioning. I think I said something to the effect of Combe. I think Siemens does everything except robotics. And he just kind of looks at me and he's like, "Don't worry, we build the software that controls a lot of these robotics," which kind of brings us here. So again, thank you to Siemens for sponsoring this theme and your continued support of the entire community. With that, Max, I want to jump back into the conversation of robot versus cobot. I was actually having this exact conversation of people using cobots for what I would generally consider more of a legacy robot application, but being able to do it in a smaller location or being able to do it without kind of all of the safety barricades and that. Do you think that we're going to see more of this going forward, or do you think we're possibly going to see some of these legacy 3, 5, 6, 7-sided robotic arms take on more of what cobots are doing to be more versatile in facilities?
It wouldn't surprise me if for most applications that aren't like spitting fire everywhere, the vast majority of them wind up as cobot type systems without the guarding. I think that especially as machine vision and I guess machine learning type solutions get better and better, and as these sensors get smaller and smaller and better integrated into the arms, there's going to be less of a reason to even buy a robot that doesn't have these capabilities baked in. Now, if you're arc welding and you're spitting fiery sparks everywhere, I think you probably still need an enclosure. Just my 2 cents. But otherwise, I think that we'll see a lot of arms that will look like regular 6-axis robots, rather, that are just safety enabled, such that like if you run into them, they stop. And if you know, and I think that's true for anything that's not being done at ridiculously high rate or very dangerous inherently. If you start having things that the arm has to move incredibly quickly, I don't really care if you if it stops really, really fast, it's still going to conk you in the head and give you a concussion. But you know, otherwise, I think that in a lot of cases we'll find cobot arms in places where we would traditionally find regular arms, and just say, well, why set a cobot? And the answer is going to be so that people can walk around it and not be worried about losing their life. Right? It's not going to be a matter of enhanced functionality. It's going to be a matter of reduced cost.
And Max, maybe as a follow-up and slightly fundamental question, I would say on cobots, because I would say my experience with them has been primarily through trade shows, right, and seeing them mostly in like a demo environment. What are the, I would say, the trade-offs? So from my understanding, it was usually the speed and typically a slightly higher like premium or cost. And could you give us maybe again some idea of like those differences, right? Is it magnitudes of cost and magnitudes of speeds, or is it becoming closer and closer to what you see in traditional robotics?
I think so. Those are definitely the two main areas, right? Speed is probably maybe 50%. Like it's not an order of magnitude, but it's probably a factor of 2. So it's substantial. And then cost might also be double, right? It's probably a factor of 2 level of difference right now. One of the areas that I'm actually super interested in is this idea of safety from a computer vision standpoint. Good luck getting this certified, but this is something that there are a number of researchers working on about identifying foreign objects in frame and in a cell, and that could be a person, and then you could automatically speed limit a system when someone walks in. And you can use these things, like you can use cobots, for instance, in conjunction with floor mats and light screens to buy you more time. So for instance, you could have a cobot running at full speed, and then when someone walks into space, it starts running at half speed. And when someone walks even closer, it runs at 10% speed. And then if someone hits it, it stops, right? And all of that could be, you know, one integrated system without the need for guarding, right?
And that's I guess that's interesting with machine vision. I guess there's some probably research that I would say like pollinates from autonomous vehicles as well, right?
Yeah.
Where you're detecting like people, and so I'm wondering how that's going to play out, because obviously there's some controversy and I would say like legal loopholes that they also need to figure out. And I think as that advances, I think that's going to open the metaphorical floodgate for all the other technologies that will use similar detection
Yeah.
techniques.
And I think it's coming. Maybe 10, 20 years from now, it'll be much more commonplace. But full disclosure, I also drive a Tesla, so you know.
Dave, what are your thoughts, or maybe some last questions on cobots specifically before we jump into a different discussion?
No, I think that the cobots are interesting, and as to Vlad's comment of most of the cobots I've seen are also on the trade show, and it's the teach pendant, it's the very super simple applications. So I think it's interesting to hear about all of the reasons why people are leveraging cobots. I would almost think that at this point, if you need a robot or want a robot, it's the which one can I get, right? Like I'll take a 6-axis, I'll take a cobot, give me anything that I can get because I need to put it on the factory floor. And that kind of brings me to the kind of the next topic of question when we look at the future. So Max, do you imagine that lead times of these things are going to go down, or do you imagine that lead times are going to stay super high because even though we can make 100,000 of them a day, a week, a month, a year now, we have demand for 200,000 of them?
I mean, I'm not a market analyst, right? So this is not financial advice, but my 2 cents is I think it will come down. I think that we need that from as major as an event the last 2 years have been. We need time for the markets to stabilize back to a somewhat steady state, and I don't think demand is going to continue to outstrip supply infinitely, right? I think. I think companies like Siemens are, very aware of the fact that there is a lot of money to be made if you can get production back up. Yep. And they are willing to pay a lot of money to do that. And there's obviously very strong market, financial incentives for companies like Siemens and Fanuc and KUKA and ABB to get production back to where it was before. And when it gets there, yeah, I mean, demand will be higher than it was before, but it's not going to be so much that we'll be waiting a year to get an arm anymore. I think that time will come down. I don't know when it will, but I think it will come down.
And as a follow-up, if I may ask, Max, someone who's looking to fill the gap, not necessarily on maybe the hardware side, but more on the skill set side, and is looking to jump into robotics, and perhaps again maybe to paint a picture of someone who's not necessarily looking to go back for 3 years in university, or maybe doesn't even have robotics in their program. What are some of the ways that you could learn or get into the robotics industry, again, at a plant level, at a systems integrator level? How would you learn robotics in, I would say, like the shortest time frame, or maybe the biggest, I would say, like value for your money today?
I mean, so it depends on what your starting point is. If you have never done anything with digital systems like programming a mechatronic system before, my first piece of advice is to buy an Arduino and start playing with it. And I mean, I realize that that's a very different beast than industrial robot systems, but that's where I started. That's where a lot of people started. There's also systems like Lego Mindstorms and Raspberry Pis and a bunch of other things. Any one of these is a good starting point for learning how mechatronics systems work. And then what you have to realize is that industrial robotics are literally a much fancier Arduino and a bigger actuator, and it's all just scaled up, right? I mean, it's basically take the controller, make it 10,000 times better, and you take the arm that you were messing with your Arduino and make it 10,000 times better, and congrats, you have an industrial robot system. Now that step is kind of big, but the only problem with that is like, how do you get into it at that level? I mean, you can build things in virtual models. You can start to learn these virtual tools, but truthfully, to learn how to use industrial arms from KUKA or ABB, if you want to learn their syntax, their specifics, they tend to be very stingy with their manuals and want to have you go to their training classes, right? So you either have to find a place that already has equipment that you can get to play around with, and that was how I was so lucky, is that I went to a site where there was equipment that I could play around with and learn how to program on. And I started with KUKA. And then I could transfer those skills, or you have to be working for a company that needs you to grab those skills. And then you need to make yourself an attractive candidate to go to those training courses and learn those skills directly from the supplier. And that's sort of an unfortunate answer. I wish there were like a really good open source community that I could say, yeah, just go here and learn from them. But the best thing I got for you is learn from the open source community in the consumer grade stuff with, Arduinos and 3D printers. And, there's lots of like microcontrol level stuff that you can do that's in the hobbyist field. And then a lot of those skills you'll find are very transferable, right, onto industrial robot systems.
And no, I think that's a very good answer. I'll point out that one of our viewers mentioned to come and see him. He's a professor of robotics and automation at a college, so I think there's going to be more and more programs at the college level. Again, because I think these robotics manufacturers are recognizing that partnering with existing colleges and universities or technical schools makes a lot more sense than
Yeah.
perhaps developing their own curriculum and running that entire kind of back end show. So as James Shuren mentioned, come and see him if you're looking into robotics. He's based
And
in
that's what
Tennessee.
I did, right? I mean, I learned through a partnership with the university with KUKA and also with Yaskawa. These robots were provided at very low cost to the university to help train people on how to use industrial robotic arms. And I mean, KUKA kind of wins because now I know how to program KUKA robots, and Yaskawa wins because I know how to program Yaskawa robots. And so if I go work for a different company and they ask me what robot you want to put in, it'll probably be one of the ones I know how to use, right? So everybody plays the game, and you got to find ways to play it yourself.
And that's a very important comment. I think not a lot of manufacturers recognize kind of like getting in the, I would say, educational space at the very core. And I can give you the same example of like Texas Instruments, who were selling, I don't know if you know, the Launchpad platform, which was kind of competing with Arduinos, but they were selling them at a loss. They were $4 shipped to your door by UPS, like an entire programming board with the cables and everything. And so the idea was that if you get exposure to engineers
The
early
lab view,
enough, it
right?
would
Yeah.
absolutely. So they lose money up front in order to gain like in the long run. But no, it's just a side comment. Dave?
No, I like that, and I think that is maybe like a sad, realistically, what most people have to go through. So, I guess, do you have? I mean, coming from I mean, you're still in the college university setting with your master's degree, Max. Do you have a good idea, like what can we as a community do to help provide better solutions and tools, because we need more robotics programmers today, and we'll certainly need more in 5 years. So if we could fast forward 5 years, what could have we done to help kind of open the community up and do a better job?
I think my 2 cents is one, the companies that provide these arms, they're incredible systems, right? I mean, KUKA and ABB and FANUC, these guys make awesome systems. It would be ideal if more of this knowledge could be openly available. I've learned just about everything I know about robotics from reading manuals. If those manuals were public knowledge instead of being paywalled, that would make life a whole lot easier for people wanting to know how these systems work and wanting to program these systems. That just, yeah, becomes, I mean, 1,000 times easier. I don't know how realistic that is. The other option that comes to mind is to make more of these types of systems available in public spaces. So things like maker spaces and community colleges. Having access to these tools up front, it doesn't even matter what vendor it is, can help a huge amount in someone's academic development. I mentioned that, I started with KUKA. The skills I learned programming a KUKA robot are basically identical to any other robot. They have different terms for the same things, but they're all the same concepts, right? You learn what a singularity is, you learn what a pose is. You can use all this stuff across any number of robot vendors, and the knowledge is transferable. So get more hardware in the hands of people that need to learn it. Is probably the single most useful thing I can say. So if there's people that run maker spaces or people that run community college labs, these sorts of things, or university labs, getting access to this type of equipment is incredibly helpful, and it'll help generate the next generation of robotics programmers.
I really wish I had access to these tools, when I was studying electrical engineering, but that's story for a different day.
Glad.
Dave, go ahead.
I already said we're getting the octopus, right?
I mean, you mentioned a 20-year time frame. It's a 20-year time
I
frame.
said within our lifetimes. I would hope our lifetimes is beyond 20 years at this point. But I think to Max's point, I think that's good advice. And I think that most professionals who specialize in any one thing that we've worked on have said very similar things. If we had better access to information, we as a community would do a better job. We can then leverage people interested in what we are looking for. I think it's a function of time and how badly is the industry hurting in the near future as to do we get to have more of these opportunities. And maybe with robots, it's a function of does the demand come down just enough and the supply go up just enough so that we can afford to send robots to makerspaces and community college, as opposed to, sending them all to manufacturing facilities who are in desperate need of them and willing to pay top dollar for that. So I think that's some very good advice. Thank you, Max. Kind of the next question is, I know you've got the next question is like content. And so I know you've got at least one podcast and a couple of pieces of reading materials. And we can absolutely go ahead and talk about the paper that you have written as part of this. So what are your suggestions of people to take a look at, Max?
Okay, so when we talked about this earlier this week, I mentioned that I'm a bit of a nerd when it comes to the kind of content that I consume on my spare time. You might have guessed by all the talk about complex mathematics and continuum manipulators that I like math. There is what I would call a recreational mathematics YouTube channel called 3 Blue 1 Brown that I heavily recommend. They also have a podcast. He talks about all sorts of interesting stuff, including, I think the single best explanation of cryptocurrency I ever had was from that channel. It really dives into the math behind why crypto works and all that stuff. But it covers all sorts of different topics, things that you wouldn't even really expect to find math in. The latest one that I found interesting was a video about how to create an algorithm to solve Wordle for you, right? Maybe you have Wordle is this game everybody's trying to come up with the word that fits the constraints, but he has a great breakdown on the math behind it and how you could code an algorithm to solve this for you. So that's my first recommendation, and I'm going to surprisingly say that's probably the lightest of reading I have for you. The other stuff is like academic journal type things. So there's the Soft Robotics Journal, which has quite a bit of good content on like research publications in soft robotics, and this is a place where, like, I think that's where, no, my paper was published in Resna, which is an assistive technology journal. But both of those are good resources to go look at if you are interested in soft robotics, segmented robotics. We didn't even really touch on segmented robotics, but that's kind of the same thing as soft robotics, but then you just chop them into multiple parts and then they can link back together. It's the shortest explanation I have for that. But there's a lot of good content there if you're willing to go actually dive into scientific journals, but that's not light reading anymore.
On a side note, we'll have those links. If you're listening to this after the live show, we'll have those links posted on the website. So if you want to check out any of the resources Max is mentioning right now, and you're either driving or listening to this on a walk, maybe, that will be posted on the website. Sorry, go ahead, Max.
No, I think that's what I had in terms of recommendations.
Awesome.
The main one I have that I actually would say, the average listener should give a shot is probably 3 Blue 1 Brown. Not everybody likes math. I get that, but it really is interesting. So,
Max, I'm just surprised you aren't wearing a T-shirt that says "I heart math." Right. Everyone, I did tell Max that we had the opportunity to get the farthest into the weeds of everyone that we've ever have. And judging by the number of people still watching, I will say that we haven't gotten too far into the weeds to absolutely lose everyone. I will also say that's the first math podcast that I have ever had suggested. I suppose we run a manufacturing podcast. It shouldn't surprise me that there are people who run math podcasts and math YouTube channels. This is a new foray for at least Vlad. He's going to be spending the weekend, one, figuring out what Wordle is, and two, how to build a algorithm to beat Wordle. And at least we now know what Vlad is going to do, as it may or may not be snowing on them in this coming weekend. But no, so that is awesome, Max. And then the last question we have for you is who should reach out to you?
So I mean, I guess anybody who's interested in advanced simulation of robotic cells, right? Most of my work is in the offline programming digital twin level. So this is things like I have, 5 robots and I need to figure out how they can all interact together. And I really need to do it right the first time. I can't afford to mess around with teach programming. I don't have the time, or I don't have the money, whatever it is. Those are areas where Siemens and that's I guess where I really excel. So that's my area of expertise. And, if you're interested in offline programming, in our offline programming solutions or anything like that, don't hesitate to reach out. And I think Dave and Vlad, you guys were going to give either my LinkedIn information, I suspect, but then also, they can forward on any questions as well to me. So.
Yeah, absolutely. And, as a same note as made earlier, because we did receive a couple more comments from our listeners on LinkedIn. If you want to have a conversation with Max, somebody talked a little bit about Node-RED and some robotic systems, Arduinos. We're going to have all those links to Max's LinkedIn channel on our website and as show notes for the podcast. So if you want to reach out to him, exactly where to find that link. Dave, any last thoughts, any questions that you want to close off?
No, Max, I think we want to thank you for such an amazing kind of kickoff to this robotics conversation and kind of the continuing of how can we do all of this virtually, right? So I think all of that is extremely exciting. If you guys are listening, I will take this opportunity to ask you to hit the like button, to drop a couple of comments below, ask Max some questions that you want us to pass on so he can answer. If you're listening on a podcast format, you guys can go ahead and subscribe. You guys can rate us 5 stars on Apple Podcasts and Spotify and Audible, because there are crazy people that listen to podcasts on Audible. Max, I like to joke. So lots of people who do podcasts ask people to subscribe. They say they don't know why it helps the algorithm. I like to joke that we do know why it helps the algorithm, but this is not that podcast. And now with Max saying here, I could be like, Max could completely rewrite the entire algorithm after watching. No, Max could completely rewrite the algorithm, and maybe we should, so our podcast goes up the charts. But we want to thank everyone. We want to thank Max. He's having some traumatic issues at the moment of having to rewrite podcast algorithms, and we want to throw a shout out and thank Siemens for their continued support of this team and all of the community. So we want to say thank you to everyone, and we'll see you all next week.
Thank you, everyone. Thank you, Max. Really appreciate it.
Absolutely.